The nice thing about monotonic and bounded sequences is that we can prove a very strong result. And that result is that any such sequence, bounded and monotonic, so it can be monotonically increasing or monotonically decreasing, but if it's a sequence in R, then we may show that the sequence is convergent. So here I will provide a proof of this fact. So let's assume that AN is a bounded sequence and that it's increasing. Well, later on you can show a similar proof for a decreasing sequence. It's just the opposite of the proof that I provide here. It's very similar. I invite you to provide a proof for a decreasing sequence. But suppose we have a bounded sequence. So AN is bounded means in particular that if we construct a set of all the values that are taken by the sequence, so let's define the set S, which takes all the values in the sequence AN, where n is just the index of the sequence, well, then this set should be bounded in R, right? Because a bounded set has an upper bound, m, and it has a lower bound, minus m. Yeah, this is how we defined a bounded sequence. This means that S is a non-empty and bounded set in R, which means that S has not only an upper bound, but it also has a least upper bound. Well, and this least upper bound is called the supremum of the set, right? So this is the least upper bound. So the sub of S, the least upper bound, the smallest upper bound for S exists. Okay, but now we just define the L, define L equals the supremum of S. And we will show now that the limit of the sequence equals L. We will show that the limit of n to infinity of this sequence equals L. Okay, how to do this? Well, in order to show that a limit of an is L for n to infinity, we know that we have to take two steps, right? So the first step is take an epsilon. Let's epsilon be larger than 0, and then we have so arbitrary but a fixed number. So now we have to show a capital N as an index such that larger indices of the sequence, the distance from AN to the proposed limit L is smaller equal than epsilon. So this is our strategy. So let's see where we end up here. So this is the graphical situation. Suppose we are here. So here is our level L. So here we have the indices, right? So on the horizontal axis, we just put down our indices n. So we have index 1, 2, 3, etc., etc. And suppose we have the supremum L. I will just provide it as a line here at a line at height L. And here you see the dashed line. And the dashed line indicates the line at height L minus epsilon, right? So L minus epsilon, we can already say something about L minus epsilon. Since L is the smallest upper bound for the sequence, L minus epsilon is not the smallest upper bound, right? So I know that L is the smallest upper bound. So L minus epsilon is not. Yeah, what does it mean that it's not the smallest upper bound? Well, if we lower the value from L, then there must be some element, AN, which takes a larger value than L minus epsilon. So in particular, what we see, this implies that there must be an index number, n, which we will call capital N, such that L minus epsilon is smaller than an and is smaller and equal than L. Yeah, all the values an are smaller equal L, since L is an upper bound for the sequence, right? Okay, so how can we show this graphically? So here we had this graph, right? So in this graph we see that there is some element, let's say it's over here on the horizontal axis, and at that point, which we will call n, we have a value an which is above L minus epsilon and smaller than L. Okay, now the proof is rather easy, since we know that an, we assume that it's an increasing sequence, right? So from this moment n on, we see that we only have increasing an increasing sequence, right? So we have, for n larger equal than n, that an is larger than a capital N, right? So uh, let's put those things in a graph. If you look at the graph over here again, if you assume the indices following this capital N, we see the values of an only getting closer to L, right? So which means that an is larger than capital An, which means that the an minus L should be closer than the distance between a capital N and L. But the distance between an and capital L is smaller than epsilon, right? So the solid line here, the difference between the solid line here and the dashed line over here, is exactly epsilon, and it's in between, right? So an is in between those lines. So the difference between a capital N and L is smaller equal than epsilon. So the following elements, the distance is even smaller. So what we have is just what we needed, is to show that we have in the long term, we have all elements within the prescribed error region, which is indicated by the epsilon term. So this is just what we needed.